Hello everyone. So this time I'm back to talk about a very cool project that I was working on. So this one is based on Andres Karpati's Autoresearch. And I will talk you through the improvement that I have done to make it more accessible. But first, let's just do a quick understanding of what the original code was intended to do. So this is the repository that Anders Karpati created. He also made a few tweets talking about his experiments and the impressions that he had on it. So the idea is actually quite simple. It is basically as simple as it is interesting, and he does a very quick summary here of how it works. So the idea, give an AI agent a small but real LLM training setup and let experiment autonomously overnight. It modifies the code, trains for 5 minutes, checks the results if they improve it, keeps or discards the changes, and repeats it until it finished the budget. So this is basically the idea. And what he did is that he used the training code to be a simplified single GPU implementation of NanoChat, which NanoChat by itself is already a simplified implementation of ChatGPT-2, GPT-2 actually, if I'm not mistaken. So this is an even more simplified version of it. So basically what he did is that he created a single Python file that keeps all of the, let's say, model training code here. So the idea is that the agents will only touch this single file, and keeping everything in as a single file would also make it easier for the agents to manage and keep it in context. Also to do the GitHub modifications. So it also has this program MD file, which basically is the instructions for the agent, basically like a skill. And this is the idea. So he kept everything very minimalistic and very simple, which is basically the core concept. So it's also something that I try to keep on my implementations and on my code changes. We'll go over the main files, but he does a very quick explanation here. So the prepare.py file is basically a set of I script that needs to run before the training actually starts. So it's a one-time data preparation, downloads the training data, and also trains the tokenizer. The train file is actually what keeps the full GPT model code, optimizers, the training loop, and everything that's relevant for the agents to do the experimentation and make the code changes. And the programmd files is the basic structures for the agent. So let's open a few of those files so that we can have a look. So the prepare program and also the training file. So prepare file is basically doing a setup. So it downloads the data. There are some helper functions here to keep everything very clean and efficient. Also the training of the tokenizer. So a lot of Python code here, but it's not very relevant, just for you to have an idea. Then there is this program MD file, which is the main one. So as you can see, it's basically structured like a skill, like any skills that you would build up for Codex or Cloud Code, any of those other models. And it has all of the instructions for the agent. So how to do the setup on the code, how to actually do the experimentation, what it can do, what it cannot do. So basically only modifying the training Python file and not touching the other files. What kind of hardness it needs to keep, like paying attention to specific metrics, and the output format that has to do. How it has to do the logs, the experimentation loop, and also has some information related to the Git commands that it will do in the end. And here the training file, it's also similar to the first one, but this has the, let's say, most very simplified implementation of the NanoChat, which is a GPT-2 actually. So basically what the agents will do is that they will do the manipulations and changing on those parameters here. So basically anything related to the model, the number of layers, the hyperparameters, and also optimizers, any kind of thing. So basically the agents are free to change anything here, run the experiment, and then see if it actually improved it or not based on the previous results. So it's actually a very minimalistic implementation of GPT-2. Okay, so once we go back here, we can see the final few relevant descriptions here, how to do the quick start, the installation. What he recommends is that it will run in a single NVIDIA GPU, and he tested on H100, which is kind of for me, and the main reason that I did this work here is that it's maybe a little bit prohibitive, only people that have NVIDIA GPUs and also a very strong GPU to run it as it was intended, right? So you can see it does the setup here. I get the script, install the dependencies, run the data preparation, and then it can actually start the training, which is a single experiment, which runs for 5 minutes each one. And the way that you would do it is that you would get an IDE like Cloud Code, Codex, or whatever you want to do, and then just do a quick prompt like this. So just for you to have a visual reference, let me open my IDE here. Okay, here I'm using anti-gravity from Google. I would just open my agent tab here, select one of the models, GPT, maybe Gemini 3.1 Pro, and send this command for this. So if I were to run this on the original Andrej Karpathy, I would do this, and then I would just trigger and start all the experimentation for Autoresearch. It will not be my case here, so let me remove it and go back to the GitHub. Okay, so project structure, if you look at the whole repository, it's only a few files, but it's only basically 4 relevant files, right? The prepare script and training script, the agent instructions, which is program MD, and the dependencies here on the Py project. He described a little bit the design choices here, basically a single file for the agent to modify, which is the training script. Fixed time budget, so he explained a little bit why he wanted only to keep 5 minutes and a specific number of steps for the agent so that they are comparable across different experimentations, different experiments, and everything is self-contained. So here it's only running into a single GPU. One file, basically one GPU, one file, one metric. So very cool idea as well. And the other main thing here that of the reason that I did my work is that for the platform support, he basically designed it to be only able to run on NVIDIA GPUs, especially on a stronger GPU. So he gives some directions here in case you want to run on smaller GPUs and what you can do, like changing a little bit the main hyperparameters related to memory consumption, maybe also using a smaller data set. But as you can see, it does not support CPU or macOS, the Apple Silicon chips here. It should be possible, as he described it, but it was not the goal here. Already some of the members of the community did some work here to support other things. But basically what I did was to make it even more accessible. I created my repository, this one here, which is a fork from the original one. And what I do here is that I enable Autoresearch to be able to run on Google Colab environment, which is accessible for anyone for free. And you can run it on GPUs or TPUs using either PyTorch, which is the original one, or JAX. So the original code runs on GPU using PyTorch. In my case here, you can use PyTorch on GPU or TPU. I use JAX on TPUs. Okay, let me go over the modifications that I did here. Basically, I try to keep the same minimalistic and simple implementation of the original one, so I only added the actual necessary files. And we have here. So it's basically the same idea, but what I added is that I also have this, instead of only the prepare.py script, I also have this prepare notebook.py, which basically does the setup required to run on a notebook, which is a little bit different than running on actual terminal script. And I also added these training files here, which the original one only had a single training file. So I created 3. This first one is in case you want to use a GPU environment using PyTorch. The second one is if you want to use a TPU environment running on the PyTorch code. And the third one uses TPU environment using JAX code. So I will just open a couple of them so you can have an idea. This is the setup for notebook and maybe the JAX TPU here. So the difference here is that it sets up a few things, basically trying to detect the kind of environment that it's running to do the installation of the necessary dependencies depending on the hardware and also the language that we'll be using, the programming language, the framework actually. And runs a few configurations here for GitHub as well that are necessary for the Google Colab environment. Of course, because it's not running on your local machine, it requires a few extra steps for you to do. Okay, so it's actually quite simple. This other file is the training file that uses the TPU hardware on the JAX framework. So it will be basically an implementation of the original code, but of course implemented on JAX to be able to run on TPUs. But it follows basically the same, let's say the same logic. I try to keep everything as one-to-one as I could here. Basically the idea, this is what I did. I will go through a quick example, but this is what you would expect. So ideally, instead of having like many researchers doing the work of fine-tuning the hyperparameters of the model, changing layers, what you will do is that over the day, maybe before sleeping at night, you would start this auto-research workflow, and then it will do like a bunch of experiments. As you can see, let me open this image here. Okay, it should be better. As you can see, for each iteration, you can see the number of experiments here. Some of them at each loop would have like some better metrics, and you can see here the modification that it was done. But at the gray here, you can also see the experiments that were not successful, did not improve based on the past ones. So it starts here from the baseline. You can see the validation metric here, and as it goes, it incrementally improves a little bit more each time, right? So each one of those experiments is a different agent that did it with a different modification. And the ones that are green, which were the ones that actually improved it, they will result into a pull request to the main repository. The pull request will look something like this. So if I go to my repository, I can see some pull requests, and they will look like this. Actually, this is for my implementation, right? So if I open one of these, you can see basically it follows this pattern of auto-research update. This one was April 11 at midnight, so 00 hours. And if I look here at file change, I can see the modifications that the agent did. So it reduced a little bit the batch size. It fixed something like this on the JAX implementation. Yeah, so basically a lot of things that I did here. The cool thing, as you can see it, is that my repository also have the Gemini code reviewer active. So my agents will do the pull request, and I also get the review from the Gemini assistant here, right? Which, by the way, another modification that I did is that on my repository, instead of running Codex or Cloud Code, I'm also using Gemini as the, let's say, LLM orchestrator, but you can basically swap it if you wish for any other LLM provider or any other kind of model. Okay, so I also added some explanations here, but it's basically the same idea. If you are interested, I also expanded here for each one of the setups, like PyTorch GPU, the modifications that I did to be able to run it on the Colab machines. As you can see, on the Colab, we have many different kinds of machines that have different hardware implementations. So some of them require you to replace some specific things, like flash attention is not available for T4 GPUs. So I did some modifications here. The same thing to be able to run the PyTorch on TPU, I had to do some modifications. So in this case, for instance, TPUs have the bfloat 16 support. So this was one of the modifications. And here also for JAX TPU support, which basically I had to do so many modifications to port from PyTorch to JAX. Okay, so let's actually go through how you can run it. And you can see in execution. Let's swap here to anti-gravity. And what I will do is that here on anti-gravity or in any VS Code IDE, you can use the Google Colab extension, which I have installed here. If you don't want to run it on IDE, you can actually run it straight on Google Colab, but I found it to be easier this way. In my case, it's already installed, right? So it's not necessary. So what I will do is go to the main entry point of this experiment, which is the notebook runner. So Karpati original code, you would just open the agent window and start here with the prompt. This will be his entry point. But here, since it's running on Colab, we need to start it here. So with the Colab extension, I just click here on select kernel, Colab, go to new Colab server. I have the available hardware here, but I will go for TPU. In my case, I have enabled the TPU V5 and also the V6 because I have Google Colab Pro account. But if you only have the free account, you will be using V5, which I will also use it here, right? So runtime of the TPU will be the latest one, so it's the most updated. And for the name of this environment, I will keep the default one, which is descriptive enough. Let's wait a little bit until it connects, and I will go through each one of the steps. So for the kernel, let's of course select Python. And after a couple of minutes, it will, maybe actually after a couple of seconds, it will start. Yeah, so it's already running on the TPU using Python. So let's start with the imports. Here it's basically some core functions to, let's say, some helper functions, something related to running commits on Git and the actually training run that happens here. So it's not very important. It's just basically auxiliary functions. Let's run it. And here is the relevant part. So for the training file, this is a parameter that you need to update depending on what you want to run. One of these three. In this case, I'm running in the TPU and the JAX implementation, so this is correct. This is the branch that I want to run from the main repository. As I'm running from the master branch, I can keep it, but if you do some modifications on the repository, you just updated this to be your new branch. And you can see that it will prompt me here for a few API keys. The first one, which is the Gemini key. Gemini key is necessary to do the prompts to the Gemini model that will be orchestrating the Autoresearch. And you can get it from AI Studio or your Vertex AI account if you have one. Then it will prompt me for my GitHub token, which in this case is necessary so that the agents can create the pull requests to your main branch. So you can see the repository URL, which is my repository. The rest is not relevant. This is the model that I'm using. I'm just using the latest Gemini 3 model at this moment. And this is the maximum amount of experiments that I want to run. So remember that each one of them will run for 5 minutes. So I will just use 3 here so that it runs a little bit faster and I can show you the results. But this is basically any number that you want to run. 3 here, it probably will take around 15 minutes, maybe a little bit more depending on the setup for each one of them. Seems to be a good time for this demo. And then we can start the repository configuration. Basically here is that I will run the prepare notebook script, which will try automatically detect the hardware that I'm using, which is TPU, and I want to run on JAX, and we'll do the setup, which it already did, right? The next one is data preparation, which runs the prepare.py script, which basically downloads the data and trains the tokenizer. So this can take a little bit more time. Okay, so data was downloaded, tokenizer was already trained, so we are ready to start training the model. I will initialize the client to do the Gemini prompts here, and then we can go to the actual pipeline. So this first cell here does some small Git setup, so nothing actually relevant here. And here it basically loads the system prompt, which is the program.md file. My program.md file is very similar to the one that Kapati wrote. Had some basic modifications here so that the agent knows basically that it has to find the training file that has the specific hardware and framework, but it's basically the same idea. So I also kept it very, very simple. And then we can go to the final cell, which is this one. It will start the training run. So let me run it and I can go through the main things here. So this is basically how the system prompt, the initial prompt is actually built. So basically some configurations here, this pointing to the training file and the actual code, which is the training script. In this case, it will be the train TPU JAX file. It loads everything here into context and sends to the model. So the model will receive this input also with the program.md, and we will actually just start to trigger the research loop. Has a lot of lines here of code, but are not very important. It's just basically handling the system prompt, doing some GitHub stuff, and detecting what to do the next step. So we can go a little bit down. And here you can see that it's basically starting everything here. It will do maximum of 3 iterations, which is the parameter that I set in the top. And this is basically the start of the first one. Something very, very interesting that I saw when I started to build this implementation is that if there are some errors in the training script, which is this file, maybe some wrong import, or if it's pointing to something different, if it's something that shouldn't exist, like a window pattern like this. The good thing is that because we are using Gemini agent, which is very good at coding, it will detect the code, it will see the error log, and it will fix for the next agent iteration. So even if you have like agents that have capacity to do web search, it could be even easier for them because they will just look at the logs from the error, do a Google search, or use its inner knowledge and fix that error. And for the next iteration, it will be already working. What the agent will be doing is that it would look at this training script, see what it can change, maybe some hyperparameters, something on the layers, and do the experiment, run for a few minutes, and starting. This first one is the baseline, so it's probably just going to run the code as it is, so it can have a baseline. So what we will do is that I will pause a little bit here and get back once the loop is finished. Okay, so here we are. So we've run the 3 experiments here. So the first one, as we saw before, it was the baseline. It printed some of the results here, the amount of time that it took, the validation metrics, also the VRAM of the TPU, and by the end it points if it was improvement or not, and the amount of the improvement, if it was. So in this case, it was the baseline, so the delta improvement was 0, basically based on the validation metric. Then it went to the second one. As you can see, after thinking a little bit, the model decided that it would try to change the device batch size. And it gives a little bit of reasoning of why it did, just to improve the utilization of the TPU hardware. It ran a little bit, and then it printed the metrics. So compared to the previous one, it was a regression. So it basically discarded this change here to the training file. Then it went to the second one, which in this case, it also tweaked a little bit the batch size, but in this case, instead of the device batch size, it decided to change the total batch size. So changing this parameter a little bit to optimize the utilization of the hardware again. It ran a little bit. In this case, it was a positive gradient, so that delta was relevant here. So it kept this change. So if I decided to run for a few more loops, it would just keep this change and do another incremental change on top of this one. Here I only used 3, so it printed out some of the summary results of the full workflow experimentation. And because I implemented here the GitHub full loop, it created another branch. In this case, it's the April 30, which is today, and 1 o'clock. So in my device, it's actually 11 o'clock at night. So 1 o'clock should be the time zone of the Colab environment machine. So it's a little bit different than my local one. It created a PR and then made the pull request. So it actually prints the link here, which is quite handy, but I can also go into the repository. But let's open here. Okay, so here is the pull request. As you can see, Gemini Code Assist already did the review, printed the summary, and I can look at the files that it changed. So basically, it only changed this small parameter. And that's also why the review from the model was very small. So I can review me as the, let's say, orchestrator of this experiment, or the human in the loop. I can take a look at the PR and merge it or not. As we saw before, I also had some other PRs here. In this case, I run for more loops. So you can see here experimentation 1, 2, 3, and 4. They all did different changes into, this one was actually a fix in an error. And here it was just tweaking a little bit the batch size to fully optimize. So probably if I run like for 10 experiments, 20 experiments, it would land in a specific batches that would optimize the hardware and then actually do more relevant code changes, right? So this is basically it. This is how you run it. Basically, it's a single entry point. You just need to use Colab environment. As a reminder, we have all of these different setups that we can use. Aside from the TPU, we can also use GPU and PyTorch on both of the hardwares, right? Make sure to take a look at the modifications that I did here to see if they are relevant. Otherwise, you can just change it. But this is the idea. One cool experiment that you can do is that in this case, we are using the simplified implementation of NanoChat, but basically you can just use any other model, right? It could be a difference transformer model, it could be a computer vision model, or it could even be any other kind of model that the Asian team will try to automate when you run it. So this is it, guys. Take a look. I hope that this work will make the cool implementation of Autoresearch more accessible, allowing people to use free Google Colab hardwares to do their own research and maybe even build a little bit upon it. If you have any ideas, if you have any questions and doubts, just leave some comments, or actually even better, in this case, just create pull requests or issues here in the GitHub that I will take a look. Thank you, guys. This was it for now, and see you in the next one.